When light passes through a substance, some of that light can be absorbed. Beer's law gives us 3 factors which can quantify the light that is absorbed as it passes through a solution. Those factors are the distance the light has to travel through the solution, or the path length B, the concentration of the solution C, and the solution's specific ability to absorb light, called the molar absorption coefficient. Let's start with the path length. If the light has to travel through more material, more of it will be absorbed. This is like when you hold up a piece of paper to the light and you can somewhat read the writing on the other side of the paper. However, if you were to add another sheet of paper, it would be more difficult to read. And the more pieces of paper you add, the harder it is to see until you hold up a notebook and it appears completely solid. The path length in our spectrophotometer is controlled by the width of the cuvette. Therefore, the light will pass through 1 centimeter of solution. The concentration of a solution, often expresses its molarity, also affects the absorbance. In these test tubes, we see a series of dilutions. You can qualitatively observe that the solution on the left absorbs more light than the one on the right, and that the intermediates from left to right transmit progressively larger amounts of light. But to really quantify why this happens, we have to think of solutions at the level of their constituent species. So if you have a solution with a higher concentration, there are more parts of solute, whether these are ions or molecules or atoms, per unit of volume. Light is made up of particles called photons, which are represented in this picture by arrows. As photons travel through a solution, there may be solute particles in their way. During such encounters, photons may be absorbed by the particles. When a photon is absorbed, its light energy goes into exciting the particle. As a result, there are less photons that come out of the other side of the solution. If we were to double the concentration of a solution, we would now have twice as many solute particles in the same amount of space, so we can anticipate that more photons will come into contact with particles, and therefore that more will be absorbed during their journey through the solution. This illustrates that solutions with higher concentrations will absorb more light. Now you might be thinking, what about the other species in the solution, the solvent? Why aren't the photons being absorbed by those particles? Well, they are, but that's why we blank the spectrophotometer, to measure the baseline absorbance of pure solvent and set this as the new 0 of absorbance. There's some interesting math that goes into calculating individual species absorbances when there are multiple species absorbing light, but those are things to look forward to beyond the scope of this course. Finally, we come to the molar absorption coefficient. The molar absorption coefficient is specific to wavelength. Think about how different substances absorb different colors of light. The color of light that something will absorb has to do with how its electrons can be excited to higher energy levels, and a lot of cool stuff goes into this, but for now let's just stick with a simplified model. White light is made up of lots of different colors. Each color has a different amount of energy it can confer. Individual photons will have one specific color, quantified by the wavelength, and energy level. So photons can be blue or green or yellow, which are all specific wavelengths, but you could not have a white photon. Different kinds of molecules have different energy needs. A molecule is very specific about the amount of energy that will get it excited. If the energy is too much or too little, the molecule doesn't accept it. In this picture, the molecules want to absorb red, so while the red photons pass through the solution, those that come into contact with molecules will be absorbed, while all the blue and green photons travel straight through the solution. The first step to finding the molar absorption coefficient is looking at a substance's absorbance spectrum, which shows how much it will absorb of each wavelength or color of light. According to this absorbance spectrum, red food coloring is most sensitive to light of a wavelength around 520 nanometers. Some substances have multiple peaks, but if you were to pass photons with a 600 nanometer wavelength through chlorophyll B, not much of it would be absorbed, so the molar absorption coefficient would be very small. Once you have determined what wavelength of light your solution is sensitive to, you will set the spectrophotometer to only measure the absorbance of a specific wavelength of light. You want your sample to be sensitive to that light, otherwise it will be more difficult to differentiate between different concentrations later on because your molar absorption coefficient will have fewer significant figures and therefore affect your precision. To find the molar absorption coefficient, we will design an experiment in which we will know or measure all of the other variables in Beer's law. The path length is constant at 1 centimeter. We will use specific concentrations as the independent variable, and we will measure the absorbance as the dependent variable. If we plot the absorbance as a function of concentration, the slope of the line is equal to the molar absorption coefficient times the path length. But remember that the path length is 1 centimeter, so really, the slope is just the molar absorption coefficient. Now we can look at the solutions of unknown concentrations, and using the absorbance in the equation, calculate the concentration. Using this example of a standard curve, if we had measured an absorbance of 0.6, we could find the unknown concentration by using the graph and plugging in known values for the equation.